scroll down and you'll have access to this study union practice exam. So it's about 2 hours, and I have a lot of questions here to get through. It's going to be a little different than the typical SARC sessions because, you know, I'll try and make it as interactive as possible, but because we have so much material to get through, then, you know, it'll be a little more like lecture style, but I'll try and make it as interactive as possible. So we could get started. I started with chapter 6 because I know that's big on probably a lot of your exams. So for question number 1, it says 900 joules of work is performed, producing 1500 joules of heat. Find the change in energy. This isn't a 0.9, by the way. That's 900. So what are the key words that we have here? We need to find change in energy. We know that work is performed and it produced 1500 joules of heat. So the first thing we have to do is find the energy, the change in energy formula. So change in energy is heat plus work. Now, it's heat plus work, but are we going to do 900 plus 1500? No, right? Because work is performed. So what we're going to plug in is Q is heat. So negative 1500 joules minus 900. Now, how did we know that it was a negative sign here? Well, we have these key words. When you see performed, that means that the sign is going to be negative instead of positive. And when you see produced for heat, that means that your sign is going to be negative. And so this is going to equal negative 2400 joules. And that's our answer. What would be some key words if it was positive? Well, let's say that heat was positive. A word that we would use would be absorbed. So if you're absorbing heat, then your sign for Q is going to be positive. So just be careful with that because they could word it in these different ways, and you know, you guys will be expected to know just based on the wording there. Sorry if that's a little blurry. I'll try and make it clearer. There we go. Okay, and also I know you guys have a lot of formulas to know for this exam, so I'll kind of box it here. This is one of the many formulas you guys are going to have that you definitely want to know. Okay? So, any questions on that one? No? Perfect. So question number 2, a balloon expands against an external pressure of 1.5 atmospheres. If the initial volume is, oops, sorry, I'll pull this out. There you go. If the initial volume is 0.485 liters and the final volume is 1.245 liters, how much work in joules is done? So with these word problems, my suggestion would be to first see what we're looking for. So how much work is done? So I'm going to underline how much work. To find how much work is done, we're given the formula here. Now on your exam, you will likely not be given the formula. We'll have to know it. So we have that W equals negative pressure times the change in volume. So in this case, what is our pressure? They give us 1.58 atmospheres. And what is our volume? Well, we have initial volume of 0.485 and final volume of 1.245. Can I just plug these into the work equation? Right. We do have to find the change in volume, but also we can't plug in the 1.45 atmospheres, right? We want it in joules. So to get into joules as our final answer, we have to convert atmospheres to joules. So this is a conversion factor that you're definitely going to want to know. So we have work equals negative pressure times change in V. Now we're going to find pressure. So we have that's negative 1.45 atmospheres. So we're going to work this out on the side. 58. 1.58 atmospheres times, we have this conversion factor here, which is 101.3 joules over liters times atmospheres. Sorry, this should be over liters times atmospheres. So now we could cross out atmospheres, right? And this is going to get us to, let's calculate that, 1.58 times 101.3. That's going to be 160.054 joules over liters. So we could plug that in now. We have negative 160.054 joules over liters, right? So now we can find our change in volume. This was pressure. Now we'll find our change in volume. So what's the formula for change in volume? Well, we have final volume minus initial volume. Final minus initial. And that's going to be, our final volume is 1.245 liters minus an initial volume of 0.485 liters. And that's going to give us 1.245 minus 0.485. That's going to give us 0.76 liters. So I'm going to plug that in, 0.76 liters. If we notice here, our units will cancel out, and are we in the units that we want in the end? Yeah, we're in joules, right? So even if, you know, maybe you forget the formula, or it's tricky how to get to the answer the way it's worded, what I usually do is I find a way to manipulate the units to get into what we want for the answer. Because there's so many formulas that we need to know, but if we know how to manipulate units, then we can always find a way to get to the answer, right? So our final answer here is going to be negative 160.054 times 0.76, right? Just this times that. And that's going to be, let me make sure that I multiplied that right. 0.75 negative, yeah, that's going to be negative 121.64 joules. And there we go. Does that kind of make sense? Yeah, perfect. So now we have question number 3. So 1.01 grams of sucrose undergoes combustion calorimeter. As the temperature rises from 24.92 Celsius to this Celsius, find the change in energy reaction for the combustion of sucrose in kilojoules per mole. The heat capacity of the bomb calorimeter, determined in a separate experiment, is this. So again, what are our key words here? We're asked to find change in energy reaction, right? And we know that this is, they tell us, a bomb calorimeter. So I'm just going to underline what we need. We have this much sucrose, and our temperature rises from this to that. And they also want us to put our answer in kilojoules per mole, and they give us this heat capacity. So what is the formula for change in energy reaction? Well, we definitely are going to be using that, so that's good. But for change in energy reaction, that's going to be Q reaction over moles of whatever we're trying to find. In this case, we're going to have to put it over the moles of sucrose, just because that's what the question is giving us. So we're going to have change in energy reaction is equal to Q reaction over moles of sucrose. But that formula you said would be for Q reaction, right? The tricky thing here is our Q going to be positive or is it going to be negative? Oh, that's okay. So For Q reaction, we have that now is equal to negative Q reaction. So when they're asking us to find reaction, we're going to have to flip our Q and make it negative. So that could be kind of something that's tricky with these exams, having to know if your Q is going to be positive or negative, because you could get two of the same answers on your exam, one being positive and one being negative, and we have to know, oh God, which one is it going to be, right? So now we could find it. So Q reaction is equal to negative. What do we use for bomb calorimeter? Is it QCat or QMCat? QCat, perfect. So we're going to have QCat. And that's just heat capacity times change in temperature, right? So negative, they gave us that our heat capacity was 4.9 kilojoules over degrees Celsius. And our change in temperature was 28.33 degrees Celsius minus 24.92 degrees Celsius, right? Because the temperature rose from this to that. So this was our final temperature. Okay, now we can calculate that. 28.33 minus 24.92. So this is going to end up being equal to negative 4.9 kilojoules over degrees Celsius times 3.41 degrees Celsius. Our units cancel. And that's going to give us, 3.41 times 4.9. That's going to be negative 16.709 kilojoules. Did that kind of make sense? Oh, so that was from the change in temperature. Yeah, exactly. So now we could plug this in for our Q reaction, this number. So that's going to be equal to negative 16.709 kilojoules over, we need our moles of sucrose now, right? So where do I have it written? I'm gonna do it on the back of a piece of paper here. So now we're gonna find the moles of sucrose. So they give us that 1.010 grams of sucrose. So 1.01 grams of sucrose. I kind of worked it out on the side so I could tell you what the molar mass is. The molar mass of sucrose is 342.3. So 342.3 grams per mole. Our units cancel, and that's going to get us moles of sucrose. So 1.01 divided by 342.3. That's going to equal 0.00295 moles of sucrose. That is a U. So now we could plug in our moles into our moles of sucrose here. So that's going to be divided by 0.00295. And our last step, we could just divide it, right? So we're in the home stretch now. 16.709 divided by 0.00295. So our final answer is going to be, I'm going to have to squish it down here, but it's negative 5,664.07 kilojoules per mole. Now we'll box the answer. Does that kind of make sense? Yeah? Perfect. Okay. So this is basically some of the math for chapter 6. Now I'm going to go into a concept question. So these are some popular concept questions. Identify each of the following processes as endothermic or exothermic and indicate sign of delta H. So what's delta H stand for? So pretty much, yeah, so delta H is enthalpy, and enthalpy, as you said, is defined as the total heat in the system. So that's enthalpy. Now they're asking us to find out if it's endothermic or exothermic. So I'm going to come down here and I'm going to kind of define these. So endothermic means that your sign of delta H is positive, right? And exothermic means that your sign of delta H is negative. So endothermic means that you're absorbing heat, and exothermic means you're giving off heat. Keeping all of this in mind, we want to decide if sweat evaporating on the skin is an endothermic or exothermic process. So what would sweat evaporating on the skin be? Is that endothermic or exothermic? Endothermic, perfect. Because the sweat is absorbing heat, right? So, you know, you're exercising, you're giving off heat, so the sweat is absorbing that heat. So this is going to be endothermic. And that means that our sign of delta H is going to be positive. Now, how about water freezing in a freezer? Yeah, perfect. So this is going to be an, oops, I spelled exo wrong. That's going to be an exothermic process, which means our change in delta H is going to be negative. So why is it exothermic? Well, when your water, what was it? Yeah, perfect. Yeah, so when you're getting cold, you're not absorbing cold, you're giving off heat, and that's what makes water freeze, or that's what makes you cold, right? So freezing is an exothermic process. Now, what about for question C, wood burning in a fire? Yeah, perfect. That's also going to be exothermic, which means our change in delta H is going to be negative. So if wood is burning, it's burning, right? It's giving off heat. It's literally on fire, so it's giving off that heat. Okay? So now we'll go on to question 5. I'll just flip my page. Oops. Okay. So 0.58 grams of magnesium metal is combined with HCl to make 100 milliliters of solution in a coffee cup calorimeter. Our concentration, this little symbol here means concentration, is of HCl is sufficient so that magnesium completely reacts. The temperature of solution rises from this to this, and they give that our density of solution is 1 gram over 1 milliliter. They have that this is equal to 4.18 grams over joules. We're asked to find the change in H reaction for the following, this equation down here. So I underlined some of the information that we need. So we need the grams of magnesium. They also give us our volume of solution, right? So this question is a little bit tricky, but if we go step by step, we can kind of break it down. So what is our formula for change in delta H reaction? Yeah, so that's going to be Q reaction over moles of whatever we're looking for, right? So in this case, what are we looking for? Moles of what? That's what tends to be kind of tricky, right? So over here, we're going to be looking for moles of magnesium. So we're going to have Q reaction over moles of magnesium. Now, likewise, how we did it in question 3 above, if you notice our change in energy reaction, we made our Q negative, right? Because QCal is equal to negative Q reaction. Well, we're going to do the same thing here. Our Q reaction is going to be negative in the end. So for coffee cup calorie meter, we have that Q reaction is equal to negative MCAT. Does it make sense, kind of like why it's negative? Yeah, kind of. So when we see reaction, when we're looking for delta H reaction, we're going to end up flipping our Q and, making it negative. So also, something important, coffee cup calorie meter, we use MCAT, right? This is MCAT, whereas bomb calorie meter was just QCAT. So that's an important distinction. Bomb calorie meter is QCAT, coffee cup calorie meter is MCAT. So now we can find our information. This M is mass, this is our specific heat, and this is change in temperature. So what's our mass? A common mistake is that students will plug in this 0.158 grams of magnesium, but actually what we're looking for here are the grams of solution, because our specific heat that they give us is solution. So how do we find a solution? Well, they give us the density and they give us the volume. So we can, like I always say, we can manipulate our units to get into mass. So we want to get into grams here, right? Because grams is mass. So we can take, I'll go on scratch paper because I'm running out of room here. So we're going to find M. So we can take our density, which is 1 gram over milliliter, and multiply it by the volume of solution, which is 100 milliliters. So our units cancel, and now we're in grams of solution. So this is 100 grams of solution. Where there's a will, there's a way. We could get to our grams. So this is going to be negative 100 grams times the specific heat they give to us, 4.18 joules over grams times degrees Celsius, times change in temperature. I'll work out the change in temperature down here. So that's equal to, it rose from temperature final minus temperature initial. Our final temperature was 32.8 degrees Celsius, and our initial temperature was 25.6 degrees Celsius. So that's going to be equal to, I'll work it out here, 32.8 minus 25.6. That's going to be equal to 7.2 degrees Celsius. So now we could plug that in, 7.2 degrees Celsius. Okay, and we make sure that our units also cancel. So Celsius cancels, grams cancel, and we're in joules, which is what we want, right? Because we're looking for, how do we know that we want joules? Because we're looking for heat. That's why. So 100 times 4.18 times 7.2, that's going to be negative 3009.6 joules. So we can plug that in. Negative 3009.6 joules over moles of magnesium. So all we need now are our moles of magnesium. So we'll work it out down here. We want moles of magnesium. So they give us that 0.158 grams of magnesium is in this solution. So 0.158 grams of magnesium. How do we get it into moles? Well, we can manipulate this by multiplying it by the molar mass of magnesium. And I can give you that molar mass. So the molar mass of magnesium is 24.31 grams per mole. So 1 mole over 24.31 grams That's going to be equal to 5.8 divided by 24.31. That's going to be equal to 0.0065 moles of magnesium. So now we could go ahead and plug that in. 0.0065 moles of magnesium. Does this step kind of make sense? Yeah. So now we could put it all together. We filled in the equation. Now we just divide. Let's roll. Negative 3009.6 divided by 0.0065. So our final answer is going to be negative 463.015.38. You could end up seeing this in scientific notation as like negative 4.63 times 10 to the 1, 2, 3, 4, 5. Oops, 10 to the 5. Right? Why did I round it to 3? Well, actually it's 2, right? So it should be negative 4.6. Because our sig figs, we have 2 sig figs right here. Over here we have 1, 2, 3, 4, 5 sig figs. Over here we have 2 sig figs, so we go by the lower one. Yeah? So we'll box that answer. Does that one make sense? What was that? Oh, so that's going to be in joules per mole. Yeah, thank you. Okay. All right. So now we can flip the page. All right. So find delta H reaction for the following reactions. So here's where we have to compare and contrast when they tell us to find delta H reaction. Over here, we found delta H reaction, but we had to go through all this math, right? Well, for this type of problem that we're doing now, question 6, we're going to use something called Hess's law. And this is going to be really big when you take chemistry 2, if you have to take it. So this is something that professors really like, because like I said, it's going to come back in future classes. Bless you. All right. So our end goal is to get these 3 equations here into a form that looks like this top equation. How do we do that? Well, we're going to multiply these 3 equations in a way that can manipulate it to get to here. We have certain rules. Rules for number 6. So if you want to flip an equation, so if we want to flip equation, we want to multiply by negative 1. So if you multiply one of these 3 by negative 1, you're going to flip the whole thing around. Also, if you multiply by a number, the whole equation must be multiplied by that number. So that's kind of an algebra concept that chemical equations, this is an equation, right? So it's like x equal to y. We could think of it like that. So if you multiply one side of the equation by something, you have to multiply the entire thing so that's still equal to each other. Oh, I spelled equation wrong. I put equation. There we go. Sorry. I'm bad at spelling. So what can we do? Well, we need to get 3 carbons on the left side, right, of the equation. So where do we have carbons? Yeah, perfect, the second one. So there are no carbons that are alone in the first, no carbons that are alone in the third, but there is one that's alone in the middle one. So we need 3 of them. So we can multiply this whole thing by 3, right? So we're going to multiply the entire thing by 3. And I'll kind of rewrite it down here. So we have 3C plus 3O2 makes 3CO2, right? So we want the carbon to have 3, but that means we have to multiply the entire equation by 3. Also, we have to multiply our delta H by 3. So whatever you multiply your equations by, you also have to do to your delta H. Okay. So now, what else do we need? We need, right, 4 of these. So we don't have any lonely hydrogen in the top one, no lonely hydrogen in the second, but we do on the bottom. So we need 4, we have 2, so we can multiply this whole thing by 2, which means we also multiply this by 2. So that's going to give us 4H2 plus 2O2 makes 4H2O. Okay, so we're looking good so far. We already have our 4 hydrogens, our 3 carbons. Now we got to do something about this top equation. Well, we need a C3H8 on the right side. We have a C3H8, but it's on the left side. So how do we get it to the right side? Yeah, perfect. So we multiply this whole top equation by -1 and our delta H by -1, and that's going to flip everything. So we're going to end up with 4H2O plus 3CO2 makes C3H8 plus 5O2, right? So we just flipped the entire thing. These came on this side, these went on this side. The good thing about Hess's law is we can always double check ourselves. So we wanted our H2, we wanted our 3 carbons, and we wanted this guy. Now we have to see if the other stuff cancels out. So we have 4H2O. That's not in our end equation. So how do we get rid of it? Well, it's on the left side of the equation here, and it's on the right side of the equation here. So they're going to cancel each other out. So these waters cancel each other out. So if you have something on the left and then something on the right in another equation, they cancel out. Our 3CO2, we have it on the left side here and on the right side here. So those cancel out. We have a 5O2 here. We have a 3O2 here and a 2O2 here. So 3 plus 2 is 5. So these cancel each other out. We add all that together. We end up with 3C, that's a carbon, plus 4H2 makes C3H8, which is our end equation. So like I said, the good thing is you always know if you're right or not because your units will cancel and all that to get to this. So now we have to find change in delta H. Well, I mean, delta means change, so I kind of said like change. But this is going to be this times -1, you just make it positive, plus 3 times -393.5, plus 2 times -483.6. So that's going to be Q43 plus 3 times 393.5 plus -1180.5 plus 483.6 times 2 plus -967.2. So we can add all this together now to get a final answer of 2043 minus 1180.5 minus 967.2. Negative 104.7 kilojoules, right? Our units were kilojoules. So we get this answer is equal to our delta H. You feel okay about that one? Yeah, perfect. Okay. So now number 7, this is our last question for chapter 6. We're doing good on time. So use standard enthalpies of formation to determine, change in delta H, well, I keep saying, so delta H reaction for the following. So what is our equation here? When we see standard enthalpy, we're going to want to use an equation that looks like this. So that little circle there means standard, like standard conditions. That's going to be equal to, this just means summation, NP, that means products, change in HF of the products, minus the sum of, this is the reactants. So this is all like calculus language. What does this even mean? Basically, we're going to look at our chemical equation. N is equal to the coefficients. So N equals coefficients. And this delta HF, well, they give that to us here, right? So let's say you're looking for the HF of your ammonia. You're just going to use, whatever they give to you. So for your exam, you could be given a really big table, and you'll just have to search through it and find what your HF is. So what we're going to do here is we're going to find our products, which is this side, minus our reactant. So our product is 4NO. So we're going to do summation of 4NO, 4 is our N, times our NO, or HF of NO is 91.3, plus our N is 6, times our HF is negative 241.8. So this is all going to get added together. Then we're going to subtract this from the summation of our reactant. So N is going to be this 4 times ammonia, negative 45.9, plus 502, so our N is 5, and our O2 is just 0. So this is going to be equal to, let's add this up. So 4 times 91.3, so this is 365.2 plus 6 times 241.8 is going to be negative 1450.8 minus 4 times 45.9. This is negative 183.6, right? So all of this is going to be equal to 365.2 minus 1450.8 plus, right, because negative makes positive, plus 183.6. Now we can add it all together. So 365.2 minus 1450.8 plus 183.6. Negative 902. And there we go. Does that one kind of make sense? Yeah? Perfect. So again, when we see standard enthalpy, we want to use this formula right here. That's kind of the key word. Okay. So that's all I have for chapter 6. Now we can move into chapter 4. So we can obtain titanium metal from its oxide according to the following balanced equation. When our kilograms of carbon react with this much of titanium oxide, this much of titanium is produced. We want to find the limiting reactant, theoretical yield, and percent yield. So I'm going to put, okay, I need scratch paper for this one. There's a long problem. I'll put this up here. There we go. Okay, so what I like to do to keep track of this is to kind of go step by step. So what is our limiting reactant? Our limiting reactant is which of our reactants is going to produce the least amount of substance. So that's going to limit the amount that we could produce. Our theoretical yield, I will be able to find that. And our percent yield, we have an equation for that as well that we'll have to go through the limiting reactant first. So we have, first we'll start with carbon. So we have that 28.6 kilograms of carbon is reacting, and we want to react it to form titanium. So how do we get from kilograms of carbon all the way into titanium? Well, we're going to first convert this to grams. So 1,000 grams over 1 kilogram. Now we're going to multiply that by the molar mass of carbon to get it into moles. So 1 mole of carbon, I have the molar mass with me here, is 12.01 grams of carbon. Now we're in moles of carbon. How do we jump over to get to titanium? Well, we're going to use something called the mole ratio. And I kind of call it our mole ratio friend because it's present in a lot of chapter 4 questions. So our mole ratio here is going to be the ratio of carbon to titanium in the original equation that they gave us. So we have 2 moles of carbon for every 1 mole of titanium. And how did I here's mole. How did I find that? Well, it just goes by the coefficient. So 2 to 1. So now we're in moles of titanium. We can now see what that gives us. So 28.6 times 1,000 divided by 12.01 divided by 2. So that's going to give us 1190.67 moles of titanium. So this is what we were able to produce from carbon. Now we want to go through the exact same process using TiO2. And what we're going to do is see which one causes us to produce less, and that's going to be our limiting reactant. So they say that TiO2 is 88.2 kilograms. Once again, we have 1,000 grams for every kilogram. We're going to multiply that by the molar mass of titanium. So I'll give that to you guys here. 1 mole of TiO2 is 79.87 grams of TiO2. Again, I just did the molar mass, so I looked at the periodic table. I found the mass of titanium and added it to the mass of 2 oxygens. Now we're in moles of TiO2, right? But we want to get into moles of titanium. So again, we use our mole ratio, right? There's our mole ratio step. That's our friend. So TiO2 to Ti, it's a 1-to-1 ratio. 1 mole TiO2, 1 mole Ti. And now we can calculate that. 88.2 times 1,000 divided by 79.87. That's going to be 1768.598 moles of titanium. So what's our limiting reactant? Oh, wait, did I multiply that? Wait, let me double check my 88.2. I think I multiplied that wrong. Divided by 79.87. Yeah, I'm sorry. This should be, I multiplied this wrong. This should be 1104.29. There we go. So what's our limiting reactant here? So in this case, it would be whichever one caused us to produce less moles of titanium. So carbon was able to produce this much titanium, whereas TiO2 allowed us to produce this much of titanium. So because this is a smaller number, it means that TiO2 is our limiting reactant. Does that kind of make sense? The limiting? Oh, that's okay. So basically what we want to do is they give us a mass of carbon and they give us a mass of TiO2 and they tell us what's produced. So we want to take what's reacting and convert it into what's being produced. So we went through and used our kilograms of carbon and reacted it so that we can produce an amount of titanium. And then we went through the same process for TiO2. We used the mass that they gave us and reacted it to manipulate its units into the product of titanium.
But why is the smaller reaction is the limiting reactant and not the larger reactant?
Oh, so the smaller one is the limiting reactant because this is what's limiting you from making more titanium. So carbon and TiO2 are reacting together. Titanium can only create this much of titanium, whereas carbon is able to make more titanium. So if we had more TiO2, we would be able to make more titanium. What's limiting us from not making more is our TiO2. Carbon can keep going, right? It can make more moles of titanium, but TiO2, it can only make this much. Does that kind of make sense?
Yeah, it's just because I went to like a geography session and I guess the way she explained it was different and like didn't really help me figure out.
Oh, that's okay. And it could be like different classes, maybe do it different, like maybe teach it different ways. This is how I do it. Maybe they just showed the math, you know, a different setup. But so we have that our limiting reactant is TiO2. A common mistake that I'll point out here is that some students will say that the limiting reactant is what was produced, but that's not the case. Your limiting reactant is the reactant. It's what's reacting in order to produce your titanium. So that's just something to be careful with. So now that we have our limiting reactant, we want to see what the theoretical yield is going to be. And they ask for theoretical yield in kilograms. So, like we said, although carbon could keep making more, TiO2 can only make this much. So theoretically, the amount that we can make is only going to be what TiO2 can give. So we'll do our theoretical yield here. Theoretical yield. I'm very bad at spelling, I'm sorry. So we're going to use the amount produced from our TiO2 to find our theoretical yield. So 1104.29 moles of titanium. We want to convert this into kilograms like the question is asking. So this much titanium, we want to get it into grams of titanium and then kilograms, right? So the molar mass of titanium is 47.87 grams per 1 mole. So that's just the molar mass. So now we're in grams of titanium. 1 kilogram over 1,000 grams, right? Because 1,000 grams is equal to a kilogram. That's going to give us 1104.92 times 47.87 divided by 1,000. That's going to give us 52.9 kilograms of titanium. So this is our theoretical yield. So theoretically, given this much of our limiting reactant, we can only make this much.
Why did you go back to kilograms?
Oh, that was just because of the question. So, yeah. Yeah, so they can ask just for grams or for any units. They can even ask for like micrograms. So I just put it in there for that. What if they did ask for micrograms? Well, it would be 1 gram is equal to how many micrograms? To the -6, right? Yeah, perfect. So we would just do, you know, if it was micrograms, it would have like 1,000,000 micrograms over 1 gram, or you could do 1 microgram over 10 to the -6. Yeah. So they could ask for, it doesn't have to be kilograms, they could ask for any of those units. We have our theoretical yield. Theoretical yield is equal to 52.9 kilograms of titanium. Now, how do we find percent yield? Well, one of my students this semester came up with something that I found to be a good mnemonic. I keep spelling things wrong. So percent yield is equal to, we say yacht. So y, percent of y is equal to A over T. So this is actual yield over theoretical yield. So if you're ever like, oh God, is the percent yield theoretical yield over actual yield, or is it actual yield over theoretical yield? We just say yacht, right? That's what helps me, because I always mix them. So we have our theoretical yield, right? We found that just now. So our theoretical yield is 52.9 kilograms of titanium. Now we need our actual yield. Do we have to do any math here? No, the question will tell us what our actual yield is, because theoretically we can only produce this much that we found, but how much was actually yielded? Well, the question tells us, so 28.6 kilograms of carbon reacts with this much of TiO2, 42.8 kilograms is produced. So this is your theoretical yield, 42.8 kilograms. Yeah, perfect. So this is our actual yield. So now we'll plug that in. 42.8 kilograms of Ti. And a good indicator that we're doing the right thing is that our answer isn't going to have units, right? It's a percent. So our kilograms are able to cancel out, and we're going to get percentage. Well, percentage we have to multiply this by 1,000, right? So otherwise it's going to give us a decimal. So 42.8 divided by 52.9 times 100 is 80.91%. If we're doing sig figs, well, it's 3 sig figs over 3 sig figs, so 80.9%. Does that kind of make sense? Yeah? So yeah. When I took this class, I always mixed them, and I was like, oh no, is it theoretical over actual or actual over theoretical? So that kind of helps. Okay. So we took this kind of really long question and turned it into something that's not that bad, right? There we go. Okay. To what volume in milliliters should you dilute 100 milliliters of a 5 molarity CaCl2 solution to obtain 0.75 molarity CaCl2? So with these types of problems, again, these are going to be really big when you get to Chem 2, so it's really good for it's really good for professors to kind of test you on them now. And also, they apply to real life. So if you're like in a research lab, this is definitely going to be something important. So it's something big if they want to test you on it. That's why professors like it. So what we do here when we see dilute is M1V1 equals M2 V2. M is for molarity, V is for volume. So what we want to do is, what volume should you dilute 100 milliliters of this much to obtain this? And we want our final answer in milliliters. So we're going to take 100 milliliters. This is our V1 of a 5 molarity solution. This is our M1. And we're going to set it equal to obtain 0.750 molarity of our V2. Now, do I have to convert my volume to liters? Because it is in milliliters, but this is you're correct, but this is a common, well, it's not a mistake that students make, it's just a lot of students will make this question a lot longer when they see a different units here. So molarity, what is molarity equal to? It's moles per liter, right? So these are in moles per liter, but this is in milliliters. But that's fine, as long as these are the same units, this and this are going to end up being the same units. So we don't actually have to convert this into liters. Right, so in this case, what we're going to do is we have 100 milliliters times, I could rewrite this as 5 moles per liter is equal to 0.750 moles per liter times our volume, times our V2. So now we're going to solve for V2, right? And I'm just going to show you how this works out, why we don't have to convert this. Basically, these units are going to cancel each other out. That's why we could do it like this. So I'm just going to grab some scratch paper. So now we solve for V2. V2 is equal to 100 milliliters times 5 moles per liter over 0.750 moles per liter. Now when you divide by a fraction, you flip it, right? So when this flips, we're going to see that it's going to be V2 is equal to 100 milliliters times 5 moles per liter times liters over 0.750 moles. Let me put this out a little bit, or too close. Yeah, see, so our moles are going to cancel and our liters cancel, and we're going to end up with milliliters for our V2. So this looks a little messy. You didn't have to go through all this. I just wanted to show you like how the units will cancel, but you could just do this M1V1 equals M2V2, right? I just wanted to prove it to you. So we have 100 times 5 divided by 0.75. Oh God. So this is going to be, oh God. Our V2 is 666.67 milliliters. Wow. I got this from the book, by the way, so.
This is chemistry.
Yeah, this is chemistry, right? Yep. So this is so this is our final answer. Here we go. Okay. So that one kind of makes sense. Okay, perfect.
I just got confused because I'm in Chem 1B,
Uh-huh.
and so we're also like, there's like, I forget the chapter it's called, but it's like, it's Boyle's equation, which is
Mhm.
also like
Mhm.
for the moles is equal to volume 2 over n. So I, for a second, thought it was that, but it's
Mhm.
not.
Yeah, so this is like a Chem 1A. There's a throwback. Oh, so
Yeah.
you're reviewing for your ACS, right?
Exactly.
Yeah. Yeah, so this is a good throwback. Yeah, this is going to be important. So, also, since you're doing your ACS, do you remember that conversion factor I told you, the atmospheres to joules?
I wrote it down. I just gotta.
Yeah, that'll be important too. so, um, so let's see. Predict whether the following compound is soluble or insoluble. So, there's a whole solubility. Well, for some of you, so for some students in the class, there's a whole solubility rules table that you have to memorize. But for some other students, it will be given to you. But what's a little shortcut here, without having to like completely memorize the solubility rules table? What is NaOH? This is a strong base, right? And strong bases, what do? They completely dissociate. So strong bases completely dissociate, weak bases only partially dissociate. So how did I know this was a strong base and that it will be soluble and completely dissociate? Well, when you have OH, OH is basically like the definition of a base. This is the strongest base you can have. When OH is paired with a group 1 or a group 2 element on the periodic table, it's going to always be soluble. So it could be paired with Na, it could be paired with K, etc. It's always going to be soluble. And this is, if you have to take organic chemistry, this is a very big reagent that you're going to end up using. So again, we have that soluble means it will dissociate. Another word for dissociate is ionize in water. Whereas insoluble means it will not dissociate. In water. So basically, if you put something insoluble in water, it's just going to stay as a solid. Whereas soluble is going to break up. So NaOH, when you put it in, is going to break up into Na plus and OH minus. So like we said, this is going to be soluble. I ran out of room here, but soluble. Does that kind of make sense? So if you look at the periodic table, look at group 1A and also 1B, or two, different periodic tables are labeled differently. It's always going to be soluble with those groups. Okay? So now question 11. What is the equation for the precipitation reaction that occurs, if any, when solutions of ammonium chloride and iron 3 nitrate mix? So this question kind of combines a lot of concepts from both chapters 3 and 4. So we have to know the formula for ammonium chloride and iron 3 nitrate, and we also have to know if it's soluble or insoluble. We have to take into consideration charges, and it kind of combines a lot having to do with the class here. So what is ammonium? Ammonium is NH4. NH4 plus is ammonium, right? But it's ammonium chloride. So ammonium's NH4 plus. Chloride, that's referring to chlorine. So ammonium has a positive charge, chlorine has a negative charge. So when you make ammonium chloride, you're going to have NH4Cl because the charges cancel. So that's being reacted with iron 3 nitrate. So plus, I'll kind of write it down here, iron is Fe. Iron is a transition metal, so we know that we can't tell what the charge of iron is going to be unless they give it to us, which they told us it's iron 3 nitrate. That means we're going to have a positive 3 charge for our iron. So whatever is in parenthesis with your Roman numerals, that's going to be your charge of your transition metal. So that's iron 3. Nitrate, the formula for nitrate is NO3, and it's going to have a -1 charge. Yeah, it's going to have a -1 charge. So this is going to be Fe NO3 3. Because if NO3 has a -1 charge, we need 3 of them to cancel out the +3 charge from iron, right? So this is also coming into play, having to know not only the name of our polyatomic ions, but the charges of them. So now it gets into solubility rules. These are going to react. Anything that has NH4 in it is always going to be soluble. There are no exceptions. So we have NH4 is going to pair with nitrate because what's paired with iron is going to be soluble. If we look at the solubility rules table, we'll see that this compound right here is going to be soluble. So NH4 NO3 plus FeCl3. How did I come up with this? Well, NH4, we said it has a positive charge, right? NO3, its polyatomic ion has a -1 charge, so we just need 1 of each, right, to cancel out the charges. For iron, it has a +3 charge. Chlorine has a -1 charge, so we need 3 chlorines in order to cancel out the +3 charge of iron. So our equation isn't balanced, but that's fine. You don't have to go through and balance this equation. All they want is to see if you're going to have a reaction or not. So how do we know if there's a reaction? Well, we said that this was soluble and this was soluble. Did we form a precipitate? A precipitate means that we form something that is insoluble, something that won't precipitate. Something that will precipitate. So anything with NH4 is soluble, like we said. And then this compound right here, based on the solubility rules table, is also soluble. So because we did not form a precipitate, we're not going to have a reaction. So remember, precipitate means you have something insoluble. We didn't have something insoluble. So we don't have a reaction because when these react and form this, our products are just going to dissociate and form this again. So we're just going to keep reacting, and we're never going to have a precipitate that will give us like a stable product. We're just going to keep breaking up and reforming. Does that kind of make sense? Yeah? Okay, perfect. Let's see the time. Yeah, we're making good time. Okay. So question 12. Find the net ionic equation for the reactions between this and that. So, net ionic, I need more paper for this one. Sorry, my paper printed weird. I should have more space there. Let's see. I'll find some scratch paper. I got one right here, because this is just a reference page. Those are my references. Thank you. Here we go. So find the net ionic equation for the reaction between HCHO2, which they tell us is a weak acid, and NaOH. So what do we know here? This is a little tricky and gets into the definition of acids and bases. So previously, in question 10 up here, we said that NaOH is a strong base, so it's going to completely dissociate, right? It'll completely ionize. So NaOH is a strong base. It completely ionizes, whereas HCHO2, they tell us that it's a weak acid. Now, what do weak acids do? They partially dissociate. So when we're finding our net ionic equation, we're going to react these two molecules together to then form a product. But it gets a little tricky because we know that this partially dissociates, but what is going to dissociate? What is going to detach from each other? We know that when this ionizes, NaOH is going to ionize into Na plus and OH minus. But what is HCHO2 going to ionize into? That we're going to have to look into the definition of an acid to find out. So we'll define base and we'll define acid. A base is something that accepts protons. A proton is an H plus atom. An acid is something that donates protons, which, like we said, is an H plus atom. You have other definitions for this regarding electrons, but the protons are what we care about in this situation to see what this is going to break up into. So basically, if you have a base, it's going to want to steal protons, whereas acids, they're going to be able to give up their protons. So if we have HCHO2 plus NaOH, what is it going to make? So because our acid donates protons, this is going to break up into H plus and CHO2. So this is going to dissociate into H plus and CHO2 negative. Does that make sense? And this, we said, is going to break up into Na plus and OH minus. So our positive is always going to go with our negative, and our negative goes with our positive, right? It's all charges. So when you're in this class and when you take later classes, a lot of times, like, maybe we memorize strong acids, strong bases, but knowing the definition always helps us to get to the answer. So this is going to be H goes with negative, so that's H2O, plus CHO2 with Na plus, that's NaCHO2, right? Negative one with positive one, they cancel out, so we could just put them together. Positive H with negative OH, we just put them together. So water and nacho. So now, to find our net ionic equation, we have to see what these are going to break up into. So for net ionic equations, we ionize everything that we can ionize to find our complete ionic equation. And then we cancel out spectator ions in our complete ionic equation to find our net. So we'll label our complete ionic equation, our spectator ions, and then we'll be able to find our net ionic equation. Right? So here, I'm just going to, this might look a little messy, but I'm just going to cross all this out here so we can work it out. So complete ionic, we'll start with here. We said this dissociates into H plus CHO2 minus plus Na plus OH minus. Does that make sense? And that's going to make water, we're not going to dissociate because we're wanting to ionize in water. Water is not going to ionize in water because it's just water, right? So we leave our water together. And now we have nacho. Are nachos soluble or insoluble? So a good shortcut here is that when you see a group 1A metal like sodium or potassium, it's always going to dissociate. So sodium, potassium, they dissociate with whatever they're connected to. So this is going to be Na plus CHO2 minus. This is so this is going to dissociate from the CHO, and the CHO is going to stay together because these aren't going to break apart from each other. It's the metal that's going to dissociate from them. Did that kind of make sense? This is somewhat of a biochemistry concept, but just know if you see sodium, if you see potassium, it's always going to dissociate. So this is our complete ionic equation. Now, to find our net, we have to cancel out spectator ions. Now, what are spectator ions? Those are ions that are on both sides of the equation, and we can cancel them out. So what do we have on the left side that's also on the right? Yeah, perfect. So we have sodium, so sodium cancels out. So sodium is one of our spectator ions, and then we have the CHO, right? So no more nachos. So Na and CHO2, those are gone. We have our H plus, that's only unique to the left side, OH is only unique to the left side, and water is only unique to the right side. So our net ionic equation is H plus OH minus makes H2O. Now does this make sense that these reactants would react to form this product? Yeah, right? So when you get to your net ionic equation, you can always get the answer right because you can always check yourself. So you want to make sure these reactants, yes, they can make my product. If you had like a barium or something in your left side and there's no barium in your products, then you know something went wrong and you got to go back. So that's the good thing about these questions. You can always get them right just by double checking. Yeah? Perfect. Is it okay if I go to the next question? Yeah? Perfect. All right. So just in case any pictures later, I could put this. There we go. So now we're on question 13. The titration of 10 milliliters of HCl solution of unknown concentration requires 12.54 milliliters of a 0.1 molarity NaOH solution to reach the equivalence point. What is the concentration of the known HCl solution in molarity? So here, what we're going to want to do is, with titration, you're basically like we're putting our acid with our base. We're titrating them together, and we're wanting to reach an equivalence point where their charges are kind of canceling each other out, right? So, and then we want to find the concentration of that HCl solution. So what we're going to do is we're going to take our molarity of NaOH, so 0.100 moles per liter, NaOH. Whoa, where did it go? Right. I just want to make sure that I'm not skipping. So we're able to take this molarity of NaOH and multiply it by our solution, which is 100 milliliters. I'm sorry, I'm looking at the wrong volume. So basically what we're doing here, again, is M1V1 equals M2V2. So molarity for NaOH is 0.1 NaOH, and our volume is 12.54 milliliters NaOH. And we set that equal to, where is it? Our M2 we have to find. So we have 10 milliliters of solution, and we have to find our M2. So this is the liters of our HCl, and this is the molarity of HCl. So now we want to isolate molarity of HCl. So M2 is equal to 0.1 times 12.54 over 10. That's going to equal 0.1 times 12.54 divided by 10. That's going to be equal to 0.1254. What units do we have here? Yeah, perfect, moles. Because over here, this was milliliter over milliliter, and this was moles per liter, so they're gonna like cancel, right? So we end up with moles. Perfect. Titration, if you see titration and dilution, these are going to be big with Chem 2. So this is another concept that professors like, because it'll apply to future classes. Okay. So evaluate the following redox reaction. And then we want to find out what's oxidized and what's reduced. Yeah, perfect. So I'll put that down here too. That's good. So yeah, perfect. So oil rig. So oxidized is losing, we're losing electrons, right? That little symbol just means electrons. And then reduced is gaining electrons. Perfect. So we want to find out what's oxidized and what's reduced in this problem here. So what are some rules that we need for redox reactions? We're going to go one by one, each atom, and well, each compound or atom, and see what their oxidation state is. And as we go through this problem, we'll see what that means, an oxidation state. So for Sn, whenever you see a lone standing atom, its oxidation state's always going to be 0. So Sn is 0. Now, why is it 0? Oxidation state refers to basically your sharing of electrons. So Sn isn't sharing electrons with anything, it just has all of it itself, so it's 0. But when we look at these other compounds, they're going to have oxidation states that aren't 0 because some atoms are electronegative, some are not as electronegative, so the electronegative ones are going to pull the electrons towards them, causing them to have, you know, a different oxidation state. Does that kind of make sense? So that's what we're doing here. Something to keep in mind also is that we're not taking the coefficients into account when we're calculating any of this. The coefficients are just there because it's a balanced equation. But when we're finding oxidation states, we don't take into consideration any of the coefficients. So, what are some rules? Well, we know that hydrogen is always going to have a +1 charge, right? So +1. That's hydrogen. Nitrogen, well, between nitrogen and oxygen, which one is more electronegative? Oxygen, perfect, because the trend on the periodic table is when we go up and to the right, we are increasing in electronegativity. So that means that oxygen is going to have the oxidation state that's going to basically be what we see on the periodic table. So oxygen on the periodic table has a -2 predicted charge, right? So oxygen is going to be -2. We have 3 of them, so -2 times 3. That's going to be oxygen's oxidation state. nitrogen, on the periodic table, it does have a predicted charge of -3, right? But we can't just go by that. Reason being, oxygen, we said, is more electronegative than nitrogen. So it's kind of stealing away some of nitrogen's electrons. Because oxygen is electronegative, it's pulling away those electrons from nitrogen. So nitrogen is going to have a more positive oxidation state than if it was alone. Does that kind of make sense? Kind of. I know electronegativity is like, that's what got me to really understand oxidation states instead of just like going by numbers and calculating it, like the actual concept behind it. So I'll put a paper here because otherwise it'll get kind of messy. So we said that, I don't want everything to get messy. So this was 0. Hydrogen was +1. Nitrogen, I'm going to say, is +n, right? We don't know what nitrogen is yet, but we're going to calculate it. Then +2 times -3, because that's oxygen. Oxygen, the periodic table is, oh, I'm sorry, I flipped it. This should be -2 times 3, but same thing. This is going to be all equal to 0. -2. So oxygen on the periodic table is -2 because, yeah, exactly. It's in group 6 of the periodic table, and it wants to have its valence filled. So it's -6 on it's in column 6, and it wants to get to 8. So that's a difference of 2, and also it's a nonmetal, so that makes it negative, right? So it wants to be like the noble gases that have 8, but it has 6. That makes sense? So we have 1 minus 6 plus n is equal to 0. -5 plus n is equal to 0. N is equal to +5. So +5 is the oxidation state of nitrogen. Does that kind of make sense? And why did we set it to 0? Well, we set it equal to 0 because this whole molecule doesn't have a net charge. So if it had a net charge of -1, let's say, we would set the whole thing equal to -1. But the whole thing is neutral together, so we set it equal to 0, which means neutral, right? If we were looking for oxygen, then, if we were looking for hydrogen, we would have to set the whole molecule equal to the charge of the polyatomic ion. So that's something to be careful with, kind of comparing and contrasting when to use 0 and when to use the charge of the polyatomic ion. Nitrogen is within the polyatomic ion, right? This is nitrate. Because nitrogen is in the polyatomic ion, we don't take into consideration the charge of the polyatomic ion. If that makes sense. That might be a little confusing how I explained it, but okay. So now we found nitrogen, we have SN. Now we're going to go to this guy, SnO2. Now Sn is a transition metal, right? So we don't know its charge. But O2, we know its charge because it's electronegative. So it's basically hogging all of the electrons for itself. So we could calculate its oxidation state. So we're going to say Sn plus, we have 2 oxygens, so 2 times -2, because -2 is the charge of oxygen. And we're going to set all of that equal to what? Yeah, perfect. We're going to set it all equal to 0, because this molecule is neutral, right? So perfect. So now Sn plus -4 is 0. Sn is equal to +4. So +4 is our oxidation state of Sn. Now we'll go on to this guy. For NO2. So in this case, what do we know the oxidation state of, and what do we have to calculate? For this one. Yeah, perfect. So we know the oxidation state of oxygen, so we have to solve for nitrogen because oxygen is more electronegative than nitrogen, right? So it's hogging all of the electrons. So nitrogen plus, we have 2 oxygen, so 2 times -2, because -2 is the charge of oxygen on the periodic table. And we set all of that equal to 0. So now N plus -4 is equal to 0. N is equal to +4. Right? And then for water, we don't really have to calculate it because, again, oxygen is going to have its regular oxidation state of -2, and hydrogen is just going to be +1. So we see that sulfur on the left side of the equation, I'll put an arrow. Sulfur on the left side is, I'm sorry, not sulfur. Sn on the left side is different than Sn on the right side. We went from a oxidation state of 0 to +4. And then nitrogen on the left side went from 5 to, on the right side, +4. So now we could compare them and see what is oxidized and what's reduced. So what happened to Sn? Did it gain or lose electrons? Well, so this is where it gets a little tricky. Electrons are negative, right? So if you're taking in something negative, you're going to become more negative. If you're losing something negative, then you're becoming more positive. An example I give is, like, imagine you had an evil twin or something. Well, if you get rid of the evil twin, the negativity in your life, you're going to have a more positive, happy life, right? So we went from 0, got rid of the negativity, and went to a +4. So that means that we lost negative things that oxidized us. So we have the Sn was oxidized. Now what was reduced? Nitrogen went from +5 to +4. So it gained negativity, right? +5 to +4, that means that it was 5 minus 1. So we gained something that was negative. So this was reduced.